of the prequest. If you're all gone for this, that, and the other thing, just watch the videos, keep up with what's going on. Homework is due Monday for everyone.
So bring it in.
Bring it in.
So we won't have a chance to get the bonus.
I had some people already turn it in, but it's not in today, no. All right, find a vector parallel to V. V is negative 2, 7. I got that from problem 1, and I want to find a vector parallel to it. Now, do not make this hard. Think about it for a second. What is this vector doing? Going left 2 and up 7? Can you think of another vector that would accomplish the same direction? It's going left 2 and up 7, so it looks like this. Can you think of another vector that might be doing the same thing? Negative 4, 14. There's one. Isn't negative 4, 14 moving exactly the same way negative 2, 7 is? Now, it's not moving, I mean, it's moving farther, it's going farther, but it's going in exactly the same direction, right? Parallel means you're going in the same direction. So that would be one answer. How did she get this?
Times 2.
Times it by 2. What if she times it by 3? Would that be another one? What if she times it by negative 1? Would that be another one? Yep, they're all parallel. So how do you get a parallel vector? Very simply, you just multiply by something. Take a scalar multiple of it. Doesn't have to be 2, 2's easy. But any scalar multiple is going to be parallel. Any scalar multiple. So if you had the vector 8, 10, and you want a vector parallel to it, you can multiply it by a half. Yeah, divided by 2, multiply it by a half. There's a vector parallel to it. You can multiply it by negative 3. There's a vector parallel to it. Any scalar multiple is parallel because the slope is the same, right? And parallel means the slope is the same. All right, number 6. Find a vector orthogonal to negative 2, 7. So now we want to be not parallel, but perpendicular. Remember, orthogonal. Orthogonal is a vector word for perpendicular. So, all right, can you think of one of those? This is our vector right here. We want to be perpendicular to it. We want to be orthogonal to it. Can you think of one?
Is that one equals 0?
Well, the dot product equals 0. So you would have to think, if that's how you were thinking, which is a great way to think about it, you got to think about dotting this with something and getting 0. 2, negative 7. Let's look at that. Does that dot product give us 0? Negative 4 minus 49. X times X, Y times Y, add them up. We're on the right track though. We got to do a little bit of switching here, but we're on the right track. 7, negative 2. Let's see, that's a negative 14 and a negative 14. That won't work, but we're getting closer. Positive 2. Now is the dot product 0? So here is one example. There are infinitely many. Think about it. If this is the vector, there are infinitely many of them perpendicular to it. This is one of them. Think about this for a second. How does this vector move? Left 2, up 7. So what's his slope? What's the slope of this vector if he goes left 2 and up 7? 7 over negative 2. What do you know about every perpendicular vector then? It will have a slope of positive 2/7. So this is a vector whose slope is 2/7. What about this one? Would this be an orthogonal vector? Yep, because it has a slope. How about this one? Would that one be an orthogonal vector? Yep, there are infinitely many of them. Any vector whose slope is 2/7 is going to be perpendicular to this one. The dot product, x times x, y times y, has to add up to be 0. And there are lots of those. Negative 4, 14. No, this is a parallel vector. This one was parallel. That was the parallel question. This was a parallel. These are perpendicular answers, some of them. This was a parallel vector. Remember, to be parallel, you just do a multiple. So here we just times by 2. To be orthogonal, you need the dot product to be 0, or you need a negative reciprocal slope. All right, number 7, find the components of the vector shown. Now, what do we mean by components? What are you looking for? X and Y, that's exactly right. So we've got this vector, magnitude 6, direction angle 28, and we want to find X and Y. So we'll say cosine 28 equals x over 6. So 6 cosine 28 equals x. And then similarly, 6 sine 28 will equal y. And we'll just type those into our trusty calculator. And I got 5.3 for x. And 2.82 for y. Is that okay with everybody? Does it make sense that those are both positive numbers? Yep, because we are in quadrant 1. So if we're not getting positive, we're in trouble. All right, find the work done when a 12-pound force in the direction of 1, 3 moves an object from 0, 0 to 10, 0. Now remember that work is an application of the dot product. Work is force times distance times cosine of the angle between. So what's happening is this. I'm going to push this chair across the room. I'm going to push it from the point 0, 0 to the point 10, 0. So what distance am I pushing it? 10 units. So my distance is 10. I am so powerful, I am pushing with a force of 12 pounds. Magnitude 12. Okay? So the magnitude of my force is 12. So here's the ground, the distance, and here's the force pushing in. Here's the angle between them. Now, how am I going to find the angle between them? Well, I know the direction of this force. It tells me that that force is in the direction 1, 3. So what do I know about that angle right there? I know its tangent is 3. So that angle is 71.56. And I'm just going to use theta in my calculator. It's 71.56. So the answer is 12 times 10 times cosine of that answer I just got. And the answer then is 37.9 1.15, what we call foot-pounds. Because we're pushing with a force in pounds, and we're pushing for a distance of feet. All right, anybody have a question about that one? All right, now we got a quiz question. This was on your quiz. Find the angle between two vectors. I didn't look at everybody's papers, but I saw some of them that had the right answer, so that's good. Your vectors are -2, 7 and 1, 2. And we're going to find the angle between them. Who feels like you remember how to do this? You got it right on the quiz. What do we do, Antonia?
You do the dot product of V and U equals the magnitude of V times the magnitude of U times the cosine of theta.
Exactly. That's kind of the general formula that pops into your head. Dot product equals magnitude times cosine. So here we go. What's the dot product of these two vectors?
12.
X times X, Y times Y. Did you get 12?
Yeah.
Magnitude of this guy. Square root of 53. Magnitude of this guy. Times the cosine of the angle that I'm looking for.
No, not the same.
So I'm going to go ahead and multiply 53 times 5. It'll just make it easier for me to type in. So the cosine of theta is 12 over root 265. So second cosine, 12 divided by the square root of 265. I got 42.51 degrees. Anybody match that?
Yeah.
Okay. Number 10. Write the parametric equations for the line through these 2 points. All right, we did this already today. We know how to do this. Write the parametric equations through 1, 5, and 2, 4. So we know that our equations are going to look like this, right? These are parametric equations of a line. So they're going to look like that. You need to fill in the blanks. All right, Patty, can you fill in any of those blanks?
Probably not. X. I think for the first blank it's -1.
This is the first blank. Could be -1. Does it have to be -1? No, but it
I'm
could
just
be
referring it back.
-1, and then this one is a
5.
5.
I'm just basing it off the point.
You could also put 2 and 4. Now, here's the mistake that's going to be made. Kids are going to fill in that fine, and they're going to put 2 and 4 here.
You don't.
No,
You find
you
out
don't.
the slope.
You find the slope. That's exactly
That I
right.
do remember.
So the slope, I got -1/3 for my slope. So now I'm very careful about where I put the -1 and where I put the 3.
3 goes with the X.
3 goes with the X, -1 goes with the Y, because slope is Y over X. Right? Okay? Let's see. All right, so next time we're together, we need to start in here and do our, then we'll move on to a pre-class. As soon as we finish that pre-class, we take a class, okay, the next step.
Wait, where do we go now?
So, be thinking about that.
We don't have what? Less effort.